Friends, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we shall learn about decarboxylation of 4 different dicarboxylic acid, and in this series the first one is formic acid. So this formic acid, if you look at very closely, so in terms of heating, it undergo decarboxylation, means carbon dioxide elimination. Question: why? If you look at this molecule little closely, this is actually a 1,2-dicarbonyl compound, and we know this because of this 1,2-dicarbonyl means these two carbonyl groups, means which is actually delta positive you may consider, are close apart to each other, and that's why 2 electron deficient carbon center in close proximity makes this system relatively unstable, and consequently what happens, upon heating they undergo elimination of one carbon dioxide and other is remain formic acid. So this formic acid is not 1,2-dicarbonyl, it's a simple mono acid, so that's why relatively stable. And second thing, CO2 eliminates from the system, so equilibrium moves towards in the right side. I shall come little later up in a details. Now this is actually 1,2-decarboxylic acid or oxalic acid. The next in this homologous series is actually malonic acid, and this malonic acid is actually beta keto acid, or you can say 1,3-dicarbonyl compound. I have already discussed about this 1,3-dicarbonyl compounds. You may visit for better learning. Now this is actually since 1,3-dicarbonyl compound, and this is not that much electron deficient like oxalic acid, but there is some special phenomena occurs through which these undergo decarboxylation. So this beta keto acid undergo decarboxylation, but student, there is a myth that beta keto acids are prone to decarboxylation, not under every condition. You remember that for decarboxylation heat is necessary, otherwise if you keep this malonic acid without heating, it will remain in that form. So what happens upon heating? So this reaction is actually a cyclic transition state is formed. What does it looks like? Means this is the OH and this is the carbonyl. So what happens in this case? If you heat, there is a 6-member cyclic transition state formation, means what happened, these oxygen lone pairs abstract this proton, so this bond comes here, consequently this opens and come back, means push pull type, and this comes here. So what it produces? It produces, this is OH, there is a negative charge. Sorry, by the way, not here, you can consider in a different way. You can say that okay, this is plus carbon dioxide, or you can represent this structure in a better way, which is the canonical form of this, means it will come, it will go, means this is actually a enol of acetic acid. Okay, I know you people may be little surprised, sir, enol of acetic acid, so it will instantly tautomerize into corresponding keto, means this part. So in this way, this part is the carboxylic acid part. So in this way, this keto enol tautomerism happens and produces this. So this is the decarboxylation mechanism for beta keto acid. By the way, I have already discussed a dedicated lecture, you may visit. Now dehydration and anhydride formation, and in this way this analog is glutaric acid. Okay, so remember OMS, sorry, not glutaric acid, I made a mistake, this is actually succinic acid. So this is succinic acid, and this mnemonic device is very good, OMSGAP, oxalic, malonic, succinic, glutaric, adipic, pimetic. Okay, so now in this case what happens? If you heat this, it produces anhydride. In previous two cases CO2 elimination was happening, in this case water elimination. And why I have taken this terephthalic acid, this phthalic acid? Because of similarity. If you count this is actually a 1 2 3 4 1,4 diacid, you can say, or you can say 1,4 dicarbonyl compound. By the way, I have already discussed a dedicated lecture on 1,4 dicarbonyl compound. Such compounds are very useful for 5-member heterocyclic preparation. You may visit. Now in this case same, so first learn about this succinic acid thing. So upon heating, what it produces this anhydride. Why? Because this is actually a 5-member ring compound. Okay, so and we know that 5-member rings are almost planar. So since they are planar, what happens that it's relatively easier that one molecule of OH and one molecule of hydrogen could be eliminated and produce this water molecule. Fine. So this, and in this case, why anhydride formation favors? Because of the reason that 5-member ring formation is both means having proper conformational orientation, that's why it forms relatively easily. And another thing, it's true that carbon dioxide is a very stable molecule, along with water is also a very stable molecule. Under this condition it comes out. So entropically also, I shall come in details. Now similar thing, if you look at this, actually this benzene 1,2-dioic acid you may consider. Okay, so this is a phthalic acid. Similarly, if you look at this succinic acid derivative, all these two carbons, carbon number 2 and carbon number 3 are sp3 hybridized. But if you look at, in this case, benzene, all are sp2 hybridized, and sp2 means planar. 5-member ring is planar. So because of this system, in this case everything is in plane. So in this case it has a higher tendency to undergo dehydration. I repeat the word in this case, dehydration, to prepare this anhydride. Okay, so in this way this anhydride is formed. Now it's a quick recalling, in summary, you may consider that decarboxylation is both entropically and enthalpically favorable. Why? Because carbon dioxide elimination is actually, it's a thermodynamically stable and kinetically very inert molecule. So what happens, that decarboxylation is both entropically and enthalpically. Since thermodynamically is stable molecule and kinetically inert, so huge amount of energy is released while CO2 forms. Point number 1. And if you look at the Gibbs free energy equation, that is delta G equal to delta H minus T delta S. So in this case, if you increase the temperature, means you are increasing the T, consequently what happened? This entropy contribution increases. And if you look at, for example, this reaction, in every case one molecule produces 2 molecules, so entropy delta S in this case is positive. So if delta is positive, increasing the T, then the delta G is mainly contributed by this T delta S term. Not only this, in addition, that delta H is further favored since significant amount of energy is released, because CO2 is thermodynamically stable. So when a stable molecule is formed, it releases energy. That's why this decarboxylation reaction is both entropically as well as enthalpically favorable phenomenon. Fine. Now third point, so in the first two cases we have observed that CO2 elimination. Fine, it's a decarboxylation, means the oxalic and malonic. But in case of succinic or this phthalic acid, what in this case, water elimination is the important phenomena. Why? Because water is a stable molecule. And another thing, elimination of a molecule is always favored high temperature, because in high temperature means the contribution of this temperature term is more. So if T increases, obviously negative delta G became more and more and more negative, and that is the condition of spontaneity. Consequently, elimination of molecule is favored by relatively higher temperature, and in this elimination, since delta S is positive, so further one step increases for delta G to be more and more and more negative. So this is the overall discussion. I believe this video may be useful. If you really enjoy my content, then please help my channel to grow. So thank you.